When performing a hypothesis test, we ultimately make a conclusion on whether or not to reject the null hypothesis and accept the alternative hypothesis. But it is very important to understand that there is a small chance, even if you do all the math correctly, that the conclusion you draw won't match the actual truth of the hypotheses just because of the inconsistencies of random sampling. So let's construct a table to kind of show what the possible conclusions we can draw are and what the actual truth might be. Okay, so there are two things that we can conclude, right? We could conclude to not reject the null and not accept rather, the alternative. So that's one thing we can do. Of course, if the evidence is strong enough, we do the opposite. We would reject the null and accept the alternative. So if we draw a sample and we have strong evidence, we would reject the null hypothesis and accept the alternative hypothesis. Okay? Now those are the things that we would do depending on the data that we draw. Okay? Depending on our sample data. But there's also an actual truth to the hypotheses, right? It could be that the null hypothesis is actually true. And the alternative hypothesis is actually false. Or it could be that the null hypothesis is actually false, and the alternative hypothesis is actually true. Okay, it's important to realize that the actual truth of these hypotheses is a little bit different than what we conclude about them, right? So if we conclude to not reject the null and not accept the alternative, and the null is actually true and the alternative is actually false, in this case, then our conclusion is correct. The null hypothesis is actually true, so we don't reject it. Okay? The alternative is actually false, and we did not accept it. Okay? That's good. That's what we want. We want a correct conclusion to our hypothesis test. Similarly, if the null hypothesis is actually false and the alternative is actually true, then we want to reject the null, and we want to accept the alternative. So in this case, if the null is actually false and we reject it, and the alternative is actually true and we accept it, in this case we would come to the correct conclusion again, right? And most of the time this is what happens. Most of the time we do reach the correct conclusion because we're good statisticians and we've done our due diligence and gotten a good sample and done the math correctly, okay? But sometimes, even despite our best efforts, even if we do all the math correctly, we come to the right conclusion. I'm sorry, the wrong conclusion. Maybe the null hypothesis is actually true, and we decide based on the evidence to reject it. Maybe the alternative is actually false, and we decide based on the evidence to accept it. This would be an error. We would be coming to the conclusion that is not what is actually happening. Okay, that is not the actual truth. We call this situation a type 1 error. Or sometimes we'll call this a false positive. We falsely accepted the alternative hypothesis when it is actually false. Okay, false positive. Similarly, if the null hypothesis is actually true, and then we choose, is actually false, and then we choose to not reject it, and the alternative is actually true, and we choose to not accept it, then that would also be an error. Our evidence wouldn't be strong enough to reject the null hypothesis, but in fact it's not true. And so if we don't reject it, we're actually drawing the wrong conclusion. This is a type 2 error or false negative. Okay, now I really want to emphasize that this is not the result of mathematical error. This is not the result of carelessness. This is a result of the inherent uncertainty in gathering a random sample. When we gather a random sample, most of the time, that random sample is a pretty good reflection of the population. And so hopefully, because it's a good reflection, we'll draw the correct conclusion. But sometimes that random sample may have too many of one or of another type of member from the population. It may not be an accurate reflection of the population. And because the sample, just by random chance, doesn't look quite like the population, we may get an error, a type 1 error or a type 2 error. Now, in practice, there's often one error we care about more, right? If you imagine going to the doctor and getting a test, and that test says whether or not you have this life-threatening illness and should take antibiotics, a false negative, that is, that you don't detect the illness, is much worse than a false positive, where you do detect an illness, but it's not actually there. In this case, you don't take that medicine that can save your life because you don't think you have that illness, okay? When in fact you do. In the case of a type 1 error, you get tested, it says you have an illness, but in fact you don't. So you end up taking the medicine, maybe you have some nasty side effects, but you're still going to be okay at the end of the day, okay? So a lot of times, one type of error may be, have a worse outcome than another type of error. Professional statisticians are trained to minimize errors appropriately. Now, a lot of times, type 1 error and type 2 error, if you try to make one small, that actually makes the other bigger, which is why we can't just set both of them to 0, right? We are going to have error no matter what, either a type 1 error or a type 2 error. Professional statisticians are trained to choose and construct a hypothesis test so it makes the worst error smaller and then the error that we can live with a little bit more bigger, and to balance that so we don't have to hopefully worry about these things too much, okay? Now, I should emphasize that these are relatively rare, and the larger your sample and the better your sample, the rarer these are. Most of the time, we do draw the correct conclusion from a hypothesis test. But sometimes, even with the best sample and the best statisticians and the best math, you are going to get an error just by random chance.